Greetings and welcome to all of our participants. There's more than 120 and counting, wherever in the planet you may be. My name is Hassan Peshhan. I'm the VP of Technology at ATEM, and I'll be moderating and hosting this webinar/panel on low latency OTT. And it is my pleasure to have a couple of very distinguished guests on our panel today. Will Law from Akamai and my colleague Mikhail Rode, who's at ATEM. Will is the chief architect within the media and carrier division at Akamai, and he's been a leading media delivery technologist. He's been involved with streaming on the internet for the last 18 years with a strong focus on client-side development. He wrote many of the early connection frameworks. He is currentently working on low latency streaming, the subject of this webinar, but also MPEG-Dash, technology evaluation, UHD distribution, CMAF, WebRTC, and web transport. Will's been a chairman of the CTA's WAVE project, that's the Web Application and Video Ecosystem project. And he's also been the past president of the Dash Industry Forum. He holds a master's degree in aerospace engineering, but I guess he found streaming to be more exciting. And he holds an MBA as well, and he was a recipient of Akamai's Danny Lewin Award, and he's worked previously for Adobe, Internet, and a series of 5 engineering and media-related startups. Very happy to have you with us, Will. He is joined in this panel by my colleague, Mikhail Rode. Mikhail received his PhD degree in 2006. He joined ATEM in 2015, where he's now the VP of Innovation. He's been leading the standardization efforts at ATEM, and he's been involved in multiple industry forums, such as the ATSC, the DVB, 3GPP project, ISO, IEC, MPEG standardization efforts, Dash-IF, and UHD forum. And he's currently managing several collaborative R&D projects within ATEM. So welcome to both of your panelists. Our agenda for today, as you can see, following the introductions, we're going to have Will talk to us about how low latency Dash and low latency HLS web networks work from the CDN perspective. And following that, Mikhail will talk to us about some of the quality implications of low latency streaming, and specifically what are the trade-offs with video quality and low latency. And he will also talk about the ecosystem more generally. And following that, we will have a couple of demos. And actually, we would very much like you, our participants, to take part in that demo. We will be sending out a link that you can use to test your own low latency streaming live as we're doing this. So hopefully that'll be a good test at a large scale. Before we dive into Will's talk, a couple of housekeeping rules here. As you notice, you're all on mute. And the reason is there's almost 200 of you now participating, so it's not practical to have everybody with audio. But what we can do, and what I do encourage you to do, absolutely, is to use the Q&A facility at the bottom of your screen. Most of you have used Zoom before, but for those who haven't, you will see an icon where you can post your questions. You can post these at any time during the talks. However, there will be a Q&A at the very end, and I will be selecting some questions, hopefully as many as I can, as time allows, and have our panelists respond to those questions. There will also be a couple of polls. We are very much interested in your opinions and your views. And as a matter of fact, we can start with one poll right now just to get a feel for what you guys think about low latency OTT and where your plans are. So I'm going to ask our host, Remy, to please show up the first poll. And let's see what, so the question is, what is your preferred OTT live latency? Is it acceptable to have more than 30 seconds of glass to glass, from camera to TV latency, or more than 20 seconds? And there's a few more options. Should it be on a par with broadcast, or should it even be faster than broadcast? So let us know, based on your use case, based on your conditions, what you think is the appropriate number. So I'm going to give you a few seconds to think about that and give us your answers, and hopefully we can share those answers while you guys have a chance to respond. Let's give it a few seconds. Okay. I see some more participants are still joining. If you're just joining us now, we're doing a little poll to see what your preferred number is for latency. I see some. Okay. So, okay, maybe Remy, if you could, okay, we still have a few more voting. Okay. I see there's still people responding. Okay. Remy, maybe we can share those numbers with our audience and see where we are at. Interesting. Okay. On a par with broadcast, that's not entirely surprising. And there are some who would prefer to be faster in broadcast. Thank you. We appreciate that. And excellent. So we'll have another poll later on at the end of Will's presentation. So for now, let me just pass on the baton to Will. I'm going to stop sharing my screen, and Will, there'll be a chance for you to start sharing yours. And without much ado, I'll let you take over here. I'll put myself on mute.
Just give me a confirmation you are sharing my screen before I launch into a blank desktop. Is the screen visible?
I don't see it yet, Will. There, okay, something's happening now. Excellent.
Good. Well, thank you very much. And good morning to you all from California. Thank you, Tim, for the invitation to speak. Low latency is certainly close to my heart, and I'm pretty excited. I have a lot of slides I want to get through, but I want to save time, obviously, for Mikhail. He's got the cool part of the talk, which is the demo. So let's get going here as quickly as we can. This slide is showing some of the latency ranges that we're familiar with in our industry today. In the industry you're in, it's going to vary the type of latency you want. Real-time communications, and it has to be sub-second. Live auctions, certain esports, we really want in the 1 to 4 seconds latency. In most live sports today, that's where broadcast latency is. Now I'm showing a US-centric latency, which is probably higher because of our cable and terrestrial-based distribution systems. In Europe, this may be closer to 3 or 4 seconds. But typically, broadcast latency is in this regime. There's a new driver for latency, which is social media, and it's a lot faster than what we used to with broadcast. People are tweeting and commenting live, and this is starting to push the latency requirements. We have responded additionally with adaptive media by reducing our signature rate. But we start getting declining benefits from this as we get shorter gaps down in the 1 second range.
Will,
sorry for interrupting. You have to close your video because we have for the.
Your audio is a bit choppy. I think a lot of people are having issues with the audio. So perhaps you can maybe turn off the video. There we go.
How about that?
It sounds better already.
Okay. Okay, we'll continue. So we've reached the segment duration, but our new approach is basically the opportunity down in the bottom corner, which is to do with chunk encoded, chunk transmitted CMAF. And this can give us latencies from 1 second and as high as we want to. And that's the regime I'm going to be talking about this morning. So you have probably seen this diagram by now if you're in the streaming industry. This is at its essence chunked encoding. It's showing a diagram of a media segment. Traditionally, we have a move index up at the start, we have a keyframe, and then we may have 6 seconds of end, which is holding our encoded audio or our encoded video. And it's only at the end of that 6 seconds that the encoder will output it to the CDN for distribution, and the player could receive it.
Will, I'm sorry, the audio is still choppy, and some of the audience cannot hear you. Would it be acceptable if we flip-flop a bit the agenda just to give you enough time to call from a landline?
Yes,
or fix the...
certainly. Sorry about that.
No worries.
Okay, we can flip-flop, and then I will find a number and I'll try to dial in with alternate audio.
So there will be some redundancy, so I will have to reduce this presentation after that. But so the idea is to talk about the ecosystem that is available, the quality implication that we will have also on the video side. So we were speaking about latency before. So So just to give an overview, because we hear about a lot of Dash industry forum. There is also another industry forum that is a CMAF industry forum. But where does it come from? Where are those standardization being done? So it's done inside MPEG. This is called the STEM group inside MPEG, where Dash and CMAF has been standardized. You may know that MPEG is already doing a codec, so they are currently working on 3 different ones: so EVC, VVC, and LC-EVC. On our side, we are also working on the Alliance for Open Media, where CMAF can be also applied to. So what is CMAF? So the idea of CMAF is to join two worlds.
Michael, I'm sorry for interrupting, but it seems that your audio is still choppy as well. So we may need for you as well to call for a number.
Okay. So this is a specification that has been pushed by Apple and Microsoft to merge two worlds, the transport stream and the FMP4. So the idea is that they concentrate on having a common format for what is taking more resources on the CDN and on the cloud, which is the chunk by themselves. So they decided to go for FMP4, which was standardized already by the ISO-based media file format inside MPEG. And there was also a specification for the manifest itself, that is the Dash. And then they let people choose whatever they want on top of the FMP4. So it can be Dash or it can be HLS. And today we are looking at something else, not join to those two worlds, but also to have a low latency as a delivery. So this has been started 4 years ago, and with a published standard in January 2018. So quite recently, 2 years ago. So they started that at MPEG 4 years ago. What is quite interesting is this particular specification. So Will is also aware of this one. So it has been published quite recently, so in March 27. So the idea of this particular specification is to provide guidelines on how to do low latency from an encoder to the player using an origin server. So they are providing different parts of the end-to-end ecosystem. So NGI-NX for the origin server, and using FFmpeg for the encoder, and at the end Dash.js as a playback. So what is low latency chunk? Just to explain what we are doing today when we are doing chunking, and what we are doing today when we are doing the low latency chunk. So when we are doing what are we doing today? So we have to wait for at least 2 seconds before sending anything, because you have to wait that we write the 2-second chunk on the file system, and then you can output this particular chunk to the origin server. So you do that every 2 seconds. When you use CMAF, low latency, here I am using 100 millisecond low latency chunk with a size of chunking that will be 2 seconds, so the same than before. So you cannot change in between resolution inside the chunk, but you can send you can preliminarily send a smaller chunk to the end user, and you can do that one by one. So you will have at least you will save a latency at least at the encoder side of 1.5 seconds in this particular use case. So what we did, because we also the idea was to test the ecosystem and to see whether there is differences in between the origin servers, the CDN, and the players. So what we are seeing today is that so we have tested with different CDNs, so Akamai, Alibaba, and AWS, and with different origin servers, so the NGI-NX, the MSL4, another NGI-NX on CloudFront, in conjunction with CloudFront in AWS, and also if MediaStore has a testing infrastructure. So the idea was to test where was the bottleneck, and so if the player doesn't support the low latency or chunk transfer encoding, then you won't have the low latency at the playback side. And another issue that we are facing is that in general, the origin server are not supporting low latency as per, so you need some dedicated way of getting the chunk, smaller chunk one by one, the low latency chunk one by one, to make them available to the CDN and then to the customers. So this is the interoperability that we have done with many different playback systems. So some only on Android devices like Visualion and Xplayer. We did test, so the Akamai player that we will be using later on is using the dash.js, so it's the same implementation in both, except that you have a small application on top of it where you can reduce the latency of the playback. We are using also a Canal Plus application that is the RX player that is also available on GitHub. TO player will be also demonstrating later on, and quite often we are also doing some test experiments with JPack and with the JPack tool from Telecom Paritech. On the CDN side, what I was saying is that we tried with different CDN vendors, Akamai, Alibaba, and AWS. And we tried different origin servers, the one from Akamai, MSL4, the one from AWS, MediaStore, and also the one from NGI. So what I will do as a comparison is that there is a full ecosystem that where you are doing redistribution from the stadium to the end user. It's quite important to notice here that what I will look at when I will compare the glass-to-glass latency is that I will have only a single encoding, so I won't have many encoding in between. So I won't have contribution, for instance, so I will take directly the SDI that will be here, and I'm just looking at this particular last mile that will give you the latency of the last mile latency of the system. How I do the comparison, just to see and to go back to the initial poll. So just to see how I will do the comparison. So I'm burning a timestamp inside the encoder that is our Titan encoder that is doing the encoding and the packaging. With Titan, I can do multiple outputs. So I'm using exactly the same video and I put that into MPEG-2 TS or I put that into Dash. And then I use the CDN and then I play back on the PC device where I can put the dash.js, or I use a professional IRD to display the transport stream. So in this particular use case on the photo that you will see after that will be MSL4 and the Akamai CDN. So in this particular example, the Titan and the professional IRD are on the same seat, so they are not far from each other. While when I'm going to the origin server, I go to Paris and then I'm using a CDN that is close to the place where I am. So the picture, so that's the picture. So on the left you have the client output. On the right you have the PC you playing the dash.js. At the bottom you have the time of the PC today. And what you see here is the one we have started to burn the timestamp on the video, and you see a delay of 2 seconds in between the broadcast and the output of the input of the encoder of the time that we have today. So just to see two timestamp, because the other one is quite small, and this is what you are having. And yes, the title is wow when it comes through. So we are getting something that is even faster when I go to Paris on a CDN with an origin server than when I play back directly the TS. So that means that we are having an infrastructure and an ecosystem that is capable of handling this today and to get something that is really fast end to end. Do you want to go now to the demo or do you want to go back to the presentation, Will?
I think, why don't we do Will's presentation if Will's ready, and then we can do a demo.
Well, I'm ready. How is this audio?
This is very good. Very good.
Okay. I can then, yeah. We're teasing people though by pulling the demo away from them. Let me go to the top share. Are you seeing the chunk CMAP
Yes.
slide there?
Yeah.
Yes.
Okay. Please do interrupt. I apologize for these audio issues. Seems Zoom's having a problem with its web-based audio, so we'll continue with this cell phone, and I'll talking as close to my cell phone as possible. I'm going to try to speed up here. So again, what I was saying was this diagram represents chunk encoding, which is really at the heart of some of the innovation that we've had in low latency streaming. The difference here is then instead of a single MOOF index, we break it up into many indices. And this index might just describe a short section of content. It could be 1 or 2 frames of video. And after the encoder's made that frame of video, it then can send it to the CDN, and the CDN can transfer it to the player for decoding. So the player can be playing the front end of the segment while the encoder is still making the back end. I have an animation here of how this might work. So this is traditional segmented delivery. We might make a 4-second video at the encoder. We're trying to get water from the faucet down to the monkey. This is our bucket analogy, essentially, but we must fill up the bucket at each stage of distribution: encoder, CDN, and player buffer before we can start decoding. The difference with low latency dash, we model it as the same buckets but with holes in them now, so that we have this constant flow of data and it's not building up or accruing at each stage of distribution. This is with low latency dash. I'm also going to address low latency HLS in this talk. I'll have this animation later on, and we'll compare what low latency HLS looks like in the same analogy. So just quickly, what is chunking reduced latency? So let's just imagine we have an encoder producing segments that 4 seconds long. Traditionally, if you're an Apple player or many media players, you're going to grab a conservative 3 segments behind live, the last 3 fully formed, and in that case, you would have 14 seconds of latency. Now, a smart developer could say, I'm willing to sacrifice my player buffer, grab just the latest segment, and that would drop my latency by more than half, down to 6 seconds. And we might say, well, we can't do better than that, but we can if we start chunking these same segments. So imagine these segments were chunked into just 4 chunks. Now, in reality, the chunks, we might have 20 times as many chunks, but I can't fit them in here in my diagram. So I'm just going with 1 second chunks in this case, where only the first chunk, the A chunk of each segment, holds an IDR. And we still need to start our decoding from that. But now, if at this time now, if we wanted to start playback, we'd only have to go back to the last available chunk instead of the last available segment. That would basically give us 2 seconds of accrued latency. And we can improve it even further, because while we can start downloading this content from 5A, we don't actually need to start with it. We could seek forward into this content and thereby reduce our latency to somewhere less than 1 second. Our second option would be to just wait for the exact start of the next segment, in which case we could grab 6A and we would have a 2-second wait, but we would also have less than 1 second latency. So just an indication that depending on whether you chunk or not and the algorithm in your player for starting, you can vary your latency from 14 seconds to less than 1 second. Now, there's some issues with this. One of the consequences of chunk-based transfer, the encoder is sending the data as it's making it. So even a client that has poor connectivity, only 3 megabits a second to the edge server, might receive a 6-second segment in these times here. A client with 10 times as much connectivity doesn't get the segments any faster because they're encoder limited, they're not throughput limited. So this causes a problem with your throughput estimation algorithm in your player, which is used to timing the download of the segment to get an idea of how much connectivity it has and therefore whether it can switch up or not. So we have to explore alternate schemes for this. There are some papers being recently published now on how to estimate throughput in the face of chunk encoding and chunk transfer. But players are going to have to adopt these new techniques. Your traditional player will simply sit there and not switch up because it'll look to it like its throughput is exactly equal to the bit rate of the video that it's playing. Another important issue that as we get into low latency is the ability for catch-up and rate adjustment, which is not something traditional players have done.
So traditionally, once you start a live player, you're stuck at a certain distance behind live. You can't increase or decrease your player buffer because you're consuming the content at the same rate that the encoder is making it, unless you alter your playback rate. And that becomes important. So we see in this chart, live latency, y-axis, time, horizontal axis. The player started with a higher latency. It sped up its playback to without seeking, it pulled itself closer to live. Then it had a problem during streaming here. And again, it was able to accelerate its playback and pull itself and hold a tight target. So the ability to adjust your playback rate and hold a tight target is a new player capability that we need moving forward. Now, it actually gives you a very nice side benefit. So if you combine this ability to catch up with a common latency target for all your players and an external time source that you can trust, because you should never trust your actual client clock, then you start getting synchronization between players. And it's a cheap and efficient way of doing it. I have 3 different devices here, different machines, all playing the same stream. You'll notice they're all within 2 frames of each other. So they're synchronized for playback, but they're not communicating directly with each other. They're simply playing the same live stream at the same delay behind live, and they're very good at keeping their latency target that way. So this is a nice side benefit as we shift to low latency and as we add rate adaptation to the player, so we can start getting synchronization between disconnected players. So as Michaela had already mentioned, I work in Dash IF. We've done a lot of work in the last 2 years to bring out guidelines for how to do low latency with Dash. So I direct you to our website up here. Under the news section, there's an item on low latency Dash. We've coordinated a lot with DVB, who have released in parallel their guidelines for how to do low latency under the DVB standard. There's a lot of information in there. It might scare you at first, but no, low latency is relatively complicated when you get into it. So how to encode latency calculations, exactly where to calculate the latency. Is it from the input to the encoder, the input to the packager, the egress from the packager, all these different capabilities. I won't go into them all on this webcast, but there's a lot of information to look. So if you are doing low latency Dash, please check out this document. Some high-level items from it that I think are interesting for this webcast. There's 2 operational modes. The first is a simple live offering, which you use duration, segment template, and dollar number. And I see a question came through in the chat on your what's the preferred addressing system. The answer is both are allowed here. So the main live offering uses segment timeline with either dollar number or dollar time addressing. The difference here with segment timeline, you typically have to refresh your manifest at the same rate as your segment duration in order to know about the very last segment. But because we want to do chunked encoding, we have to publish that manifest update ahead of when we normally would. So this is a nuance to segment timeline that a Dash player is going to have to take into account, or it will not play low latency with segment timeline. And the same is true for segment number. We have an availability time offset. So the answer is you can use both addressing schemes. The segment timeline will give the advantage of seeking backwards or for accurate ad insertion. But if you just want to play a live stream at the live edge, which is a very common use case, then segment template dollar number is a simpler means of doing it. And the demos we're going to show you today are all using that. There are some new service descriptions. There's a latency element. It gives you a target latency that the player should try to achieve. And it also, interestingly, gives you a min and a max. So the idea is that not all players should be at the latency. Poorly connected players may struggle to keep it a level. And instead of having them in a constant rebuffer loop, you would rather prefer that they chose a slightly higher latency that was still within the service description guidelines. There's also playback speed elements, so whether you can control or limit how much rate adaptation the player will do to correct its latency. There's also a requirement for a UTC timing element because timing becomes very important, certainly on the Dash side, and you cannot trust the client clock. They drift too much. It's okay to get low latency with just very small segments with Dash. Your segment should be at least 30% of your target latency, so you'll have 3 of them before you try to decode your content. But the preferred method, and again, all the demos we're going to show today use chunked encoding. There's something new and pretty exciting coming through to Dash out of the 4th edition that I thought I'd just preview on, and it's something called resync elements. Now, they're a little bit of a strange name, so let me explain what it is. So here we're looking at 2 CMAP segments. They're each 4 seconds long. They're each composed of two GOPs. There's one at the start and one in the middle. Now, with traditional CMAP, we know nothing about this GOP in the middle. This is actually a point that we could switch to or start decoding this content at. But with traditional CMAP or Dash, we're not told about it. So basically, resync elements is a way to tell the player about the presence of these internal chunks that the player may be able to start decoding or speaking at. So this gives you some benefits for fast start. You could start at this segment, or more importantly, for quick switching and resynchronization after a buffer underrun. So how does the player find them? Well, there's two ways. One, the encoder can make a binary map of each resync point, but that doesn't really work well for live because you'd have to be making it behind the fact, and with live, your players are playing at the leading edge. So the other way is signaling in the manifest itself. And this is a pretty interesting way to do it. So I'm showing an example here. Here's one of these new resync elements in the Dash manifest. And by combining the information in the resync element with information that's already in the manifest, the player can figure out the min and max byte range at which this resync element might exist. It doesn't know it exactly because of variable frame rate and variation in encoding, but it knows a byte range. So it could make a range request to the CDM, retrieve this portion of the content, then it has to parse it in order to find that segment so that it can find that chunk so that it can place it into its decode buffer. And usually you can set a marker true to say, hey, this is a resync point using a box parsing algorithm, which is much more efficient than a traditional binary parsing algorithm. So resync elements, I think, are a pretty exciting feature coming to Dash in the near term. Check them out for low latency. I'm going to switch over now to low latency HLS, which, if you remember, back in June of last year, Roger Pantos announced it at Apple's WWDC. We're 1 year down the pipe now, and in fact, he's just released it into the core spec for HLS. But I'm going to go through some of the concepts in case you're not aware of them. It is designed to accommodate latency in a very similar range to what low latency Dash is doing, which is sort of 1.5 seconds and up from there. Certainly neither of these formats is good for sub-second transfer outside of the laboratory. It's backwards compatible. It preserves all the characteristics of HLS, which is good and bad. One of them is that you have to download a text file before you download every segment. And as you'll see, this starts increasing our request rate. It's ABR switchable, and it supports add metadata, and it's cacheable by CDN. So we like it for delivering low latency content at scale. Now, the beautiful thing is they chose exactly the same chunk encoding that Dash is using in order to prepare the content for distribution. Apple don't call them chunks, they call them parts, but they are relatively synonymous if you stick within a CMAP construct. So the parts cannot be one frame in size. That's too small like Dash chunks are, but typically they're 250, 300 milliseconds and up. And if you look at the Apple reference stream today, it's actually a 1 second part. So it's a new word here. It just means this little grouping of a move index and an MDAT section, and maybe several of them together. They also describe these parts explicitly in the playlist. So normally you might have one media segment described like this in the HLS media playlist. Now it describes every single constituent part. There might be 4 or 5 or 6 or 8 parts per segment. And each has a unique URL, and each is cached independently as an object by the CDN. There's a new notion with HLS for low latency that there's now more intelligence required at the origin server. So it used to be you could stand up a straight Apache Nginx server, modify nothing, and it was just basically file delivery to be able to play HLS. As we shift to low latency, there's a much stronger requirement that the origin server is intelligent. It needs to understand when parts and segments become available, because it has a notion called blocking, which is if the client asks for one of these parts ahead of its availability, instead of responding with a 404, the origin is intelligent and says, I'm gonna block my response, and the moment this part is available, I'm gonna release it down to the client. So this helps the client with its timing. In fact, it's a very powerful and efficient timing mechanism, but it puts a lot of responsibility onto the origin that wasn't there previously with HLS. So quick look at the manifest structure. Here's a low latency manifest. We notice the server advertising, or the packager actually, or the origin, that it understands server control. So it's saying there's some features that I support that other origins may not. We have a new attribute, which is our target duration for our part. And we see a conventionally listed segment, and then we notice that our parts are now listed. There's two ways to list them. Independent parts contain IDRs. They're points at which the player can start decoding the content. So this is important at startup and for quick switches. And parts are only described for the last 3 segments in the media playlist. In other words, those 3 segments trailing the live edge. After that, the part descriptions fall out of the media playlist. Another very cool feature, and in fact, the secret to interop between Dash and HLS for low latency is that Apple in its spec allows for the byte range addressing of parts. Now, I don't have time to go through this full animation, but you can see the sequence. It's describing a part as a byte range into a full media segment. And the player is able to make range requests into these segments in order to retrieve the individual parts. And this is exciting because when it starts off playing a segment, for this particular example highlighted in yellow here, when I make a range request from 0 and an open-ended request forward, I'm essentially making the same request that the Dash low latency player is making for that segment. And that is going to be how we can achieve interop between these 2 formats. And also, if you remember LHLS, the industry version of HLS that came out last year in an attempt to bring low latency to HLS in a very consistent manner with Dash, well, this byte range addressing is pretty much, from the client side, going to look a lot like the LHLS. Now, Apple originally came out requiring H2 push to try to solve some of the timing issues with these very small parts, but they did away with that based on industry feedback, and they've come up with a very powerful solution, which is basically a preload hint. So as the packager says, I'm done making part 0 in this case, it advertises that part 1 is being made. It's not ready yet, but it's being made. And you can go ahead and the player can go ahead and request it ahead of time. And because of the blocking capability in the origin will block until this is ready and then return it immediately to the player. So the players are going to make 2 parallel requests now. It makes a media playlist update to get the next part, and it makes a part request for the part that's been hinted to it. And this works very well in practice, and it's also very compliant with CDN-based behavior today. We don't have to change. There's been a lot of thrash in LLHLS recently. The software is only available in the beta versions. It's still not available in your major macOS update. I'm hoping perhaps after June of this year, or maybe in September, we will get it in mainline. But you can go download beta versions, see them right now. Apple has released software encoder, packager, and origin service. So you can set up an origin for yourself, and I encourage you to download it at this link and test it out. There's also a live reference screen from Apple, which is interesting to look at. Go check that. And as a reminder, just on April 30th, 2 weeks ago, they updated their HLS spec at IETF to fully include LLHLS. So it's no longer a beta implementation. It is fully part of HLS. Now, comparing the 2 formats, if I go through them quickly, you'll notice that there's actually lots that's common between the 2. They both require chunk encoding. They support the same latency range. They're backward compatible with older players. They're cacheable by CDN. They support the same DRM. They both support ad insertion, multiple codec types. They allow ABR playback, and they both are conformant with HTTP delivery. So there's a lot that's similar between these 2 formats. However, let's look at some of the differences. Now, I'm using green dots and red dots to basically denote yes. Green is yes to a feature. It doesn't necessarily mean it's good. It just means that the format supports that feature. So Dash uses chunk transfer for delivery of the content. Apple does not. They have a mandate that you must only ever deliver parts at line speed, meaning as fast as the connection allows. So the part has to be fully available before you can transmit it, whereas in Dash, it can be under production. This is a core difference in the delivery. LLHS describes the internal segment structure because it lists every part, whereas Dash doesn't. Now, the resync elements of Dash will essentially solve this problem, but because they're not fully out there in the industry yet and they're pretty new, I'm including them as a difference. Apple, you have to refresh the playlist with every chunk. This makes a large increase in edge hit rate for CDN distribution. Apple always delivers the object at line speed. This helps it with throughput estimation. So then Dash has the problem that how can we calculate our throughput when we're getting chunked transferred content? LLHLS supports TS segments, although honestly, I don't know anybody in the industry who's using TS with low latency HLS. Everybody is standardizing on CMAP or ISO base media file format segments. So that's a bit of a non-op there. LLHLS, even though it doesn't use push, it still requires HTTP2 for the last mile. In fact, I did a test last week where we turned off HTTP2. The Apple player just refused to play the low latency stream. And then we turned HTTP2 on and it played it. So it's definitely checking for it requires an H2 connection from the edge server in order to play low latency on Apple's AV Player AV Foundation. You do require the smart origin to modify the playlist. The Dash doesn't have that requirement. You can have essentially a file system serving files and it will still work. And Apple is deterministic startup, meaning I have a whole slide on this in a separate presentation, but it means it's a little more accurate to start up, whereas the Dash player has to do some guessing because of this internal segment destruction. So then just two more slides.
A couple of minutes, Will. Yeah.
Okay, last two slides, here I go. So I showed this one before. I just want to be able to compare the three formats. So this is traditional, adaptive, segmented. We're filling up our full segment at each stage of distribution. That's CDN, handing it down to the player, and then the player handing it down to the decode buffer. And as I showed, low latency Dash looks like buckets with holes in them. Well, LLHLS looks like this, looks like really quick and small buckets. So we're still doing the handoff, but we're doing it 4 or 8 times faster than we were doing it previously with our standard segmented delivery. Maybe that will help some people figure out sort of the difference in the distributions. And then my last slide here is just a difference in request rate. So imagine I've got a 6-second segment with chunks or parts that are 333 milliseconds, so 3 of them per second. My Dash client is downloading 1 6-second for audio, 1 6-second segment for video every 6 seconds, and that's essentially 20 requests per minute to CDN edge. Now, an LLHLS client playing the same content, the request rate is going to look like this. It's probably not, certainly Zoom can't screen scrape fast enough. The request rate will be 720 requests per minute CDN edge. And every request has a cost. So at some point, we're going to have to reconcile the distribution cost of LLHLS against that of Dash. But the request rate is certainly one of the issues. The larger your parts, the lower the request rate. So I think we're going to see parts moving away from the several hundred milliseconds and up to the 1 second mark to make this request rate a little more rational. And with that, I will return my presentation. Let me stop sharing.
Thank you, Will. Appreciate that. That was excellent timing, by the way. And on that note, since you finished with the HLS versus Dash comparison, we have a second poll to run, and that is, you guessed it, LLS versus HLS. So the participants, please let us know if you plan to support low latency Dash only or low latency HLS only, or both of those, or neither of those. So we'll give you a few seconds to respond to that poll. In the meantime, while the participants are doing that, Mikhail, perhaps you can just start your demo and share your screen in preparation for the demos. So let's give a few seconds for audience to think about that. And by the way, I acknowledge all of you who have sent in questions, excellent questions, and we will certainly pick some of those up during the Q&A session right after demos. Interesting, both LLA. Okay, very well. And in terms of LL Dash only versus LLHLS only, there seems to be more or less a tie, and 84 people think both. Excellent. Well, thank you for that response, and thank you for your participation in that poll. Mikhail, I think we're all ready for your demos.
Yeah, so I will go for the demo. Can you hear me well now?
I can hear you well. And by the way, there is a link that I believe Remy has shared with the audience.
Yeah, so I will go back to the link just after, just explaining what we will have. So I want to change the slide. So we are using how to play the low latency dash. So we will be using for this demo the dash.js. So you will see a page from Akamai that is using dash.js. I will be also using on my side the TO player and the player from Canal Plus. The playback is better on Chrome. So if you want to test, it's better to try with Chrome. It's more stable. Alternative playback will be to use JPack. So we use Mock2 demo. So you have so it will display the time of your PC, and you have a link to HTTPS time.is that will give you the drift of your PC compared to the NTP sync. So if you have a drift, you may have to resync your NTP, your clock with the NTP server, just to have the true difference in between what we burn in the video and what you will have on this particular display of your time of your PC. So we use the Akamai playback that is using the very last version of dash.js that has been published last week, 3.1.0. So that's why I just moved the 3.0.3 that I was using last time. There is something that is quite nice, is that you can reduce the latency of the playback, meaning that you can put that, so it will be at 3 seconds in the link and you can put it back to 0.5. Which is the minimum that we can use. So we will be able to go down to this particular number. The other thing is that you have a graph on the other side that will give you some information on the chunk itself, on the buffer. If you are up, if you have the buffer that is upper than the latency, and you will see also the latency of the system. So you will see what also Will was mentioning is that you are not going to the next chunk to accelerate. So you will see the player that is accelerating. It's not disturbing you, but you will have the audio. If you have the audio on your side, you will have the audio, and you will see that on the audio you will hear the audio accelerating. So the audio is a bit tricky, but for the video you won't see that we are really accelerating the video. But you are not going to the next chunk to accelerate. So you are trying to go to the edge without going to the next chunk, just accelerating the video. So I have two versions. So the one that I'm using is the typical H.264 quality preset that we have in our Titan Live that will be at 6 megabits per second. So I'm using quite long chunk just for the demo. So it's 10-second chunk, and for the low latency chunk, I'm using 100 milliseconds. So in my case, it will be, so it's a 50 FPS content, so it will be 5 frames, the size of the low latency chunk. You can see with the debug mode of Chrome, you will see the download of each of the chunk, and you will see that there is a progressing bar that will be that 100 milliseconds after 100 milliseconds. So the link is this one. So if you go to the web page, sharing, yes, so you should see that. If you click on akamai.js, so that's the high quality preset. So you cannot put a URL here. It's not working when I put that, but so that's the URL that is currently working. So this is the high quality one. I have a latency of 3 seconds, and I can click with the start button. And here, so you see the progression of the chunk on the right. So they are quite long. So it's 10-second chunk, and then you go to the next one. But you see the progression is 100 milliseconds by 100 milliseconds. So then, if I open the other one, that will be the time here. And if I check that I won't have drift on my side, so it's really close to the NTP. You can take a photo in between the two, and it should be around 4 seconds in this particular case, but I haven't reduced the latency here. So what I was saying is that I can reduce the latency. So it's going, so you see that the latency is not going to, so I put 3 to 0.5 directly, but it's not going to 3 to 0.5 directly. So it's taking some time to go to reach a point that we are willing to reach. which is 0.5 second latency for the player. And you are seeing in the end the latency that should be around 2.5 to 3 seconds in between the timestamp that I put just after the SDI on one side, so just after the SDI card and to the glass, to the display. So I see a difference of 2.5 to 3 seconds in this particular use case. And I have something stable for the playout at 0.5. So really close to the edge. So the player is not having a huge buffer for displaying the content. So I have different playback. So I can use, on my side, I will use several just to see that we are having several of them working today. It's not something that is just a research as of today, so it's getting real. So this is the Canal Plus player here. So you can see the buffer. And you are having something that is a bit higher than what we are having with Akamai, but it's really close also to the edge in the end.
So, Mikhail, we have some very good questions coming from the audience. I'd like to leave some time for that as well, just to be aware.
So I go to the other link that is also interesting, just to see what is the latency also of the encoder. So I'm reducing the latency of the encoder. So that's the second link that you are having on your side. So it's ultra low latency. So I put the encoding at 8 to have the same visual quality. So I'm using 25% more bitrate than on the other side. So we'll go to 3 seconds. And then I can reduce again the latency of the playback. And in the end, if I look the difference in between the two, I will be really close to 1.5 second latency end-to-end. So the encoder is in Rennes, the origin server is in Paris, and the CDN is, I suppose this one is in Paris as well. So, and you are getting end-to-end latency of in between the encoder and the display of around 1.5 seconds. So I think we can go to the question, because some of the questions will be answered by some of the presentations that I have at the end, but that are not.
Yeah. Thank you, Mikhail, for that demo. Hopefully, it proves that this is real. There are a lot of questions. I'll try to go through as many as I can through the limited time. The first one actually is a two-part question from Stefan, and I will pose this to Will, if that's fine. He's asking, is there a preferred manifest for low latency, for example, time-based segment templates? And his second question is, what is the impact of dynamic ads insertion? Will, why don't you take a shot at that one?
So, yeah, I try to answer that during my talk. Both methods are acceptable. Most people today are using segment template dollar number just because it's very simple. It's a very clean way of describing the content. However, I do know if people are starting to use segment timeline, it does have a much higher manifest request rate against the edge. The segment template dollar number, you only have to give the player the manifest once. But with segment timeline, you're giving it every segment duration. Your player in both cases has to be relatively sophisticated. For your ad insertion, if your segments are, say, 2-second segments and your chunk shorter and you're okay with inserting your ads at your segment boundaries, then I think segment template dollar number is sufficient. But if you want to start inserting ads midway through segments and with frame accurate precision, then probably a segment timeline, dollar time or dollar number would be your solution. But the vast majority today are using segment template dollar number with an ad duration.
Thank you, Will.
What was it? Yeah. Okay.
And Mikhail, I'll push the second question towards your way. It's from Sebastian, and he's asking, do you need a push packager, or can this work with a standard pull packager model as well?
if you want to make it available, so the player is working on a pull mode. So we could do both, but at the moment, all of us are doing the same. So we are using the origin server in the push mode. So it simplifies the way we are pushing the content.
Okay.
And from the Akamai side, we support both. We have a push origin. So that's the demo that Mikhail's showing right now. It's pushing to an Akamai origin. But we also, you don't need to use that. You can simply use our CDN for delivery and provide your own origin as well.
Excellent. A couple of questions kind of asked about the overhead of low latency. Is it significant or not? Perhaps will or
it's just a box, so it's not significant in the end in terms of overhead.
And a related question is there a cost difference between the current, quote unquote, high latency mode and the low latency mode that we're proposing here? Is there a penalty to be paid in terms of cost?
I want to point out to people that you can play a low latency stream with high latency. So we could be playing these same streams 45 seconds behind live if we wanted to. So it's just how it's encoded in packet. The actual latency is determined by the player, not by the encoder. So you can distribute a stream and have some clients playing it with low latency and the rest of your clients, say in LATAM or somewhere with more challenge, playing it in higher latency. The cost overhead is the cost of packaging those extra move boxes, which, as Mikhail indicated in our test, is about, it depends on the bit rate of your content, but it's about 1% to 3% is your overhead. So not a large cost penalty in return for a lot of functionality.
And a good segue, you mentioned LATAM. One of our audience members is in LATAM, and the question they're asking is, what is it, is it possible to have high quality, low latency in LATAM countries where the infrastructure may not be as good as some other parts of the world?
So the answer is, you can't have your cake everywhere. If you're on a poor connection that is variable, it's the variability of the connection that hurts low latency more than anything else. So well-connected clients in LATAM can play low latency, and people can be testing the link right now, and if they're there, they can let us know what their playback's like. But the reality is the player needs to adjust. If it finds itself on the end of a poor last mile, there's nothing the encoder can do to help it. The player has to pick a higher latency that is tolerant of the level of variability that that player is experiencing in its last mile. So we need to get away from this rigid notion of one latency for all clients, because not all clients can achieve the same low latency at the same time, even when playing the same stream.
Okay. One question from Pesh at AT&T. What is Apple's reasoning for requiring HTTP2 for the last mile? How close are the major CDN providers to enabling HTTP2 at the edge? Maybe Will.
So, yeah, Akamai has HTTP2 for the last 2 years. It's fully available on all our offerings. And in fact, the demo that Mikhail is doing will use HTTP2, may even use HTTP2 plus Quick, actually, which is sort of H3. Why does Apple require it? Because there's other features of H2 regarding prioritization of segments within an H2 request they really like, because they like to be able to prioritize the playlist request against the media segment request when both are going to the same host name. There's also a ping frame, which is a timing mechanism within H2 that the client can use to figure out the RTT between itself and the server, and again, to help with its timing. Even though they're not using the push attributes, they do like other characteristics of H2 that they feel are important to get good quality, low latency playback.
I'm going to put in one more question from Marcio. What is the impact of HTTP retransmission comparing low latency dash and low latency HOS?
So is he talking retransmission at the TCP protocol level? I'm not really understanding the question.
It's HTTP retransmission. I guess my guess is if there's packet loss at this point.
So that's independent of the protocol. Packet loss is packet loss. One difference is Apple is moving very small objects very quickly. And typically, if you want to get higher throughput, certainly with TCP, because of TCP windowing, you want a larger object. So you will get a higher throughput if you reuse your TCP connection and you have larger objects that you're moving. So there's a bit of a throughput penalty you pay by moving small objects very quickly, and these may be more subject to loss. But essentially, TCP loss will affect both formats equally. It's a file transfer system at the end of the day.
Well, we have plenty of other questions, but unfortunately, we're already 4 or 5 minutes beyond our allotted time. So I'd like to thank again both Will and Mikael for excellent presentations and also for their answers to these questions, and also our participants. Thank you for taking part, making and enriching our seminar, and thank you for your questions. And with that, I'll be closing the session. Thank you again. Appreciate it.